Well, hello everyone. Back here with another video. The probably the last one in this series for a little bit, related to my ITS2300 data networking class, or really for anyone who wants to get a little bit of information, a little bit of knowledge about how the internet works. All right, so in this one, we're going to talk about TCP. So the namesake of the book we're using, and I had to do things a little bit differently here. So again, the book for the class, or if you want to follow along with this particular guide, is the TCP Illustrated Volume 1 book by Stevenson Fall. And normally I kind of scroll through the table of content listing and point out sections that kind of give the initial overview. With TCP, that's not so easy. As you can see here, there are, let's see, is TCP, and the book starts with chapter 12, and then goes on through 13, 14, 15, 16, and 17. So 2, 4, 6 chapters in the book cover TCP. So really tough to just kind of scroll through there to give an idea of what to look for. So what I can do is put this up on the screen. Let me make this a little bit bigger. And for those of you in the class, you've seen this. It's also in our content management system in Blackboard. But the gist of this is that the first chapter, chapter 12 on TCP, is really the one you want to look at. It has all of the, it describes all the basic functionality that makes TCP what it is and why it exists. Then there's a couple of sections in chapter 13 that's called TCP connection management, which gives you some details about how this mechanism actually works. So chapter 12 gives a really good overview of all the stuff that's needed to make TCP work. There's a lot of detail that needs to go into actually making things work. And so 13 talks about how you actually set up a connection in TCP. Chapter 14 talks about retransmissions. TCP is reliable, so it has to have a concept of retransmitting data that was lost somehow. And so there's a couple of sections I suggest in chapter 14 that talk about how that works, how some of the details work. Chapter 15 talks about TCP data flow and window management, particularly what's called flow control in TCP. And then chapter 16 talks about congestion control. And again, in those chapters, just a couple of sections will give you the information you need to sort of have at least a working understanding how this works. So as always, let's jump into our Jamboard here and talk a little bit about what makes TCP unique from anything else you've looked at before. So remember that in our layered protocol model, we have an application somewhere that wants to transmit data. It relies on a transport layer to mediate between the application and what in the internet is always IP, the network layer. Right, and so in the transport layer, the application could use UDP, which is just a simple overlay on top of IP. Has no concept of reliability. It simply does its best packet by packet to deliver data. So if the application needs reliability, if it needs to actually make sure the data gets there properly to the other side, the application would have to implement its own retransmission strategy. And that's wasteful, because that means every application developer would have to come up with their own way of doing things. They wouldn't all interoperate really well, so lots of reasons not to do that. So if an application needs reliability, at first step, it will pick TCP as its transport protocol of choice. So TCP being reliable means that at the TCP layer, as part of the design of TCP, which is built into most, all modern operating systems, it has to be a concept of retransmitting things, and that complicates things, right? UDP just adds some information to the data the application hands it, and then hands it off to IP to transmit the information. TCP can't do that. TCP has to be capable of retransmitting information. So in the simplest case, TCP might have a packet here. And TCP packets are called segments, and I transmit it. And if for some reason somewhere in the network the data gets lost, the receiver would just not do anything. There are different ways of implementing reliability. I'm not going to go into all of this, otherwise this video is going to get way too long. So in TCP and in all modern protocols I'm aware of, the receiver reacts when it does receive a packet correctly. All right, so if the packet is lost, the receiver sees no activity on the network. It does nothing. The sender waits a period of time. That's where some of the detailed sections later on come in. How long should you actually wait? But the sender will wait for the TCP sender will wait for a little bit. It says, I should have heard back by now. I haven't. I'm going to send that packet again. This time, let's say it arrives and an acknowledgement gets returned, and so then the TCP sender can go on to the next packet and send that. Now, if that's all we did, it would be very inefficient because we'd wait a lot of time. Let's assume that most of the transmissions are successful. We would be sitting around waiting for a long time just for the receiver to respond. So this is not really what TCP does. What TCP does is it asks the application to basically give it a long string of data. So the application has no concept of TCP segments. It just produces a long string of bytes. TCP will now go in and create TCP segments, packets for all practical purposes. So it'll break the data up into segments. It will then, based on some rules inherent in the way TCP operates, decide that it has a window, an allowance, to send a certain amount of data. Let's say it's these three. So now what will happen is TCP will send those three packets, this one, and this one, pretty much one after the other, and then wait for an acknowledgement. And if everything goes well, it will say, okay, this first packet was received, so I can now shift my window a packet further back, and that brings this fourth packet into play, and I can send it out. This operation of moving the window over once a packet has been correctly received, it gave this mechanism the term sliding window. All right, and so one of the quirks in the specifics of how TCP is designed is the way the receiver reacts, right? So let's say the receiver got that first packet and it got acknowledged, as you can see. Let's say the next packet never made it, but then the next two, remember this, the sender sent this first one, it got acknowledged. I'm not going to draw all the arrows here. It slid the window over. It has already sent the second and third. Now it sent the fourth packet. So let's say those two made it as well. There is no way in TCP for the receiver to say, I got 1 and 3 and 4, but not 2. All it can do is say, I did receive 1. And even when these come in, all it can do is keep repeating, I have 1. And so it's up to the sender to be smart and say, okay, if you keep saying that, regardless of what else you received, I definitely need to send 2, and then I might wait and see if that actually clears everything up. So let's say this packet gets retransmitted and finally makes it back. At that point, the receiver will actually say, yeah, I got 4, because it now has a full stack or a full list of data that all fit together. So so without add-ons, which got bolted on later, and which can be used but aren't terribly commonly used, TCP has no concept of selectively acknowledging what was or wasn't received. It simply has a concept of a cumulative acknowledgement, where I basically tell you I've received everything up to here correctly. Okay, so that's the basic mechanism. Let's talk a little bit about some of the details, and again, I want to keep this video to some reasonable length. So to implement this, the way because remember, TCP thinks of everything as just a long list of bytes, and then it breaks it down to packets. TCP labels a packet not by a packet number, but it actually labels the first byte. So if this is 1,000 bytes, and this is the first 1,000, this would be byte 1, 2, all the way through 1,000. This first packet would be labeled 1. The next packet being sent out would be labeled 1001, because that would be would be the 1001st byte. This would be 1 through 1000. This would be 1001, and on. So that's one. So that's one thing to watch out for. The way this numbering actually works is just for lots of reasons. TCP works on the concept of a connection. So if the machine that serves as the client for a connection, it's just whoever initiates the connection, and then automatically the other one becomes the server. So if a client application wants to create a TCP connection, it will send a packet to the server with something called the SYN, or synchronized flag set. Flags are, and I'm not going to go into the details of the content of the TCP segments, TCP header. SYN or SYN is one of the flags, one of the one bit fields in the packet that you can set. And that alerts the server that, hey, you need to set up memory to receive data. We need to talk about what our first sequence number will be, because I don't want to start every packet at 1. I want to start at a random number, so that for various reasons, security being one of them, I don't want people to be able to guess and interfere with my connection because they know what my next packet is going to be labeled as. So I need to transmit all that stuff. The server then will reply with a packet that has both the SYN flag and the ACK flag set, ACK for acknowledgement. All right, and so that exchange, and there's actually a third packet that's technically necessary. That's an acknowledgement without the SYN set coming from the client back to the server. It's called the triple handshake. At this point, there's a relationship between the two, which involves the setting up memory buffers and counters and timers and all the different things that needed to make TCP work. And remember, the client and server these are bidirectional, so they can each send data to each other. So there really are 2 TCP flows involved in this connection. So I want to just, I'm going to keep this video relatively short. So I'm going to just touch on one other thing. Once this connection is established, TCP will do 2 things. It will try to maintain flow control. Remember, it has this window that it with a particular size that it slides over as data is acknowledged. The size of that window can be variable, and in TCP it is. And so, from the perspective of flow control, let's say the client contacted the server, but there's really data flowing from the server to the client, like would happen if you went to download and update a program or something. So the server is now sending data to me, the client. I can, in the reverse direction, as I acknowledge data, I can tell the server, make your window smaller, or you can make your window bigger, depending on how much memory I have, how quickly I can store things on disk, whatever is required. So flow control is a concept where the machine that receives the data can control how much data flows in and how quickly, so its resources don't get overwhelmed. The second concept here is congestion control. So what happens here is, if, again, they use that same data flow, so the server is sending data back to the client. What if some data gets lost here? Because the network is too busy. The data is flowing through a bottleneck in the network, and routers are too busy, and they discard data basically because they have no memory to store it. So now data's been lost, not because the client couldn't handle it, not because it's damaged, but because the network's too busy. And we don't want that. We need to react to that correctly. In this case, I can again use the sliding window, make it smaller, so I send less data at a time. But this time, that control is entirely here at the server, which is sending the data. So the flow control. In flow control, the client told the server, hey, slow down, or you can speed up, whatever it may be. In congestion control, the server, which is sending the data, looks and sees if it has to retransmit data. It didn't get acknowledgement, its timer went off, it knows it has to send a segment of data again. When it does that, it also shrinks the window. That slows it down, hopefully protects the network a little bit, lets the congestion dissipate. And so after things have been working properly for a little bit, the server can then very cautiously make the window a little bit bigger, send a little bit faster, in the hopes that there's enough capacity to handle that. And if it sees a retransmission event, if something's lost, it has to retransmit, it will shrink the window again, and so on. So this single sliding window mechanism built into TCP can serve both of these very different functions in operating TCP. Now, this was a super high-level, quick overview over what TCP has to accomplish. There's lots of detail, which is why there's 6 chapters in the book on it. So you can read and read and read and read. But if you want to sort of understand this level, the list of sections that I showed at the beginning is where you want to go. So again, I hope this was useful. If it was, then please let me know, and we'll make some more of these in the future. We'll see you in the next video.